Hello everyone. Welcome to this new session of the Journal Club. Today we have two speakers. The first one is going to be Ziyang, and the second one is going to be David. And so we will start with Ziyang, and Ziyang is a PhD student, a second year PhD student at the University of Heidelberg. And today she's going to talk to us about model independent tests of molecular gravity. So feel free to start whenever.
Thank you for the introduction. So good morning to everyone. And as you can see from the title, there's essentially two keywords in my talk. The first one is modified gravity, which is interesting to explore in many contexts, for instance, in the background of cosmological tensions. And the second keyword is model independent. So let's start from the first keyword, modified gravity. We already know that Einstein's general relativity is a massless spin-2 field theory with 2 degrees of freedom. And when we say modified gravity, it means we add more degrees of freedom. This could be a scalar, could be a vector, or could be a tensor. And if we only consider scalar perturbations, the most general perturbed metric in the Newtonian gauge read as follows, with the 2 scalar degrees of freedom quantified by these 2 geometrical perturbations, these 2 free functions, psi and phi here. And if you put these 2 functions into Einstein's field equation, what you get here is essentially this cosmological Poisson equation, which tells you how matter falls into the gravitational potential. So phenomenologically, in order to describe modified gravity and deviations from this standard Poisson equation, people introduce these 2 free functions. The first function is eta, which is the ratio of these 2 gravitational potential and tells us the deviation of geometry, the deviation in kinematics, and the second function mu, which is essentially the effective gravitational constant and tells us the deviation in dynamics, the deviation in the forces. So in general relativity, these 2 functions both goes back to 1, but in principle, they could both depend on time and scale. For instance, in the Hornetsky theory, eta and mu have dependency on both time and scale. So this means if we are able to find a way to measure these 2 free functions, and we trust our measurement, but the k scaling differs from the one of Hornetsky, then we are confident to say, okay, this whole class of Hornetsky model can be ruled out. And then the second keyword is model independent. So the motivation here is, even though from our current observations, we know that, for instance, from Planck, we are able to constrain the various cosmological parameters in a quite precise way. But the results are always based on some assumptions of assuming a cosmological model, for instance, assuming a lambda CDM. And here we would like to draw conclusions on cosmological observables, for instance, the expansion rate, the growth rate, in a fully model-independent way in order to derive more accurate estimations, and finally to study the geometry and dynamics of the universe. And when we say model-independent, we mean independent of a cosmological model, or we also don't consider cases where there is a parameterization that is non-physical. So in our case, we don't assume the spatial curvature of the universe. We don't make assumptions on the shape of the power spectrum. We don't assume the background expansion, or we don't assume any initial condition of the universe. But of course, we have to make some assumptions. But all the assumptions here are already outside of the scope of assuming a cosmological model. For instance, the only assumptions are, for instance, the equivalence principle, the cosmological principle, or assuming the energy momentum conservation of the matter component. So at local scales, if we want to test gravity, the local gravity experiments can always be hidden due to the screening mechanism. So this indicates in order to test gravity, we need to measure at cosmological scales. For instance, if we take a look at the equation of motion for a generic particle, we will find that the dominant term actually depends on the velocity of the object. For instance, for small velocity objects like galaxies, this last term dominates this psi term, and we can relate psi to the peculiar velocity field of galaxies through this Euler equation, which tells us how is the change of the spatial of the geometry of the universe with a flow of particles. Well, for relativistic velocity objects, this first term dominates. So we can extract this lensing potential, this psi minus phi term, from lensing observations. And the conclusion here is we need to combine the information from both small velocity galaxies and relativistic velocity photons in order to test gravity. And now let's first start to look at which model-independent observable are we able to extract from galaxy clustering. So galaxy clustering basically tells us how many galaxies can you count inside each pixel. And all the information that we can receive is essentially on the redshift of each galaxy in each pixel and the incoming direction of the photons. For the galaxy number count fluctuations, it is mainly contributed by these two components. The first one is a term proportional to the matter density contrast, and it's related to a B function, which is the galaxy bias, which is fully unknown. We don't even know whether it's depending on gravity or not, so we don't have any knowledge on the bias term. And the second term is redshift space distortion due to the existence of the peculiar velocity of galaxies. Therefore, for the galaxy power spectrum, it has this additional mu dependency, where mu is just the angle between the line of sight and the separation of the galaxy pairs, because the inclusion of this redshift space distortion breaks the isotropy if we only consider the first term. So in the end, from galaxy power spectrum, we are able to isolate two model-independent quantities. The first one is this combination of parameters, b times delta m, and we call it amplitude. And the second one is this r, because this is related to the redshift space distortion. So these two functions are essentially the two quantities which we can extract in a model-independent way from the galaxy clustering environments. Then from weak lensing, it tells us how much the galaxy images get distorted due to the presence of some matter which is between the background galaxy and between us, between the observers. And what we can extract is essentially this alpha, the deflection angle, which is directly related to the lensing potential. On the other hand, if you combine these two cosmological Poisson equations, then you obtain the expression here. And from the right-hand side, you can further isolate a third model-independent observable. And we call it L here because this is related to lensing. If H0 is able to be measured in a model-independent way, and if the expansion rate E can also be measured in a model-independent way. Firstly, for H0, because it only depends on the local expansion and basically there's no assumption on the cosmology. So H0 can be considered safely as a model independent quantity. And what about the expansion rate E? So if we measure the expansion rate from standard candles through the apparent magnitude of your standard candle, which can be related to the luminosity distance. But for the right-hand side, this spatial curvature omega k and expansion rate E is essentially nested. So this means if we want to infer the expansion rate of the universe from the standard candles, we have to somehow make assumptions on the spatial curvature. And people normally assuming this is a flat universe. So here we would like to get rid of that assumption and we make use of the so-called Alko-Kopczynski effect. So this is essentially relates the mu angle and the wave number k to a reference cosmology. And the only assumption is essentially the cosmological principle without any assumptions on the spatial curvature. And furthermore, from this AP effect, you are able to infer the expansion rate E and also the angular diameter distance in a fully model-independent way. So for a quick summary, at the linear level, one can basically extract 4 model-independent observables with 2 extracted from galaxy clustering, the amplitude and the redshift space distortion, while the other 2 extracted from weak lensing environments, the lensing L, and furthermore, the expansion rate of the universe. So the next goal would be, can we find a way to combine all these observables in order to isolate the quantities that we are interested in, namely in this case, eta and mu, these two functions. because they are relevant to test gravity. So interestingly, one can essentially find this unique combination of parameters in order to describe your measured eta directly extracted from observations, which essentially only depending on the expansion rate L and R. And also get rid of delta M0, which contains the information of the initial condition of the universe, and also get rid of the bias function, which we are fully unknown. So from here, we can see that eta is indeed a model-independent quantity to test gravity. So from this eta, we can then compare with some theory predicted that we would like to test with, for instance, test Hornetsky and possibly to falsify it. So that is basically the idea of testing eta. And before testing mu, because if you remember, mu essentially describes the effective gravitational constant and describes the change, the deviation from the standard Poisson equation. And in general, given a modified gravity theory or given any dark energy model, you can map the corresponding mu for that specific model. For instance, in the coupled quintessence scenario, where there's a fifth force existing between the dark sector, between dark matter and dark energy, and mu in that case is essentially equivalent to 1 plus 2 beta squared, where beta is essentially just the coupling between the dark sector. But one thing I want to emphasize here is that essentially mu is not an indicator of modified gravity. For instance, in some scenarios, for instance, of the clustering dark energy scenario, where mu deviates from 1, but this is purely due to the intrinsic property of dark energy. But in this case, eta still remains 1, so there's no modified gravity here. So that is something that we should be careful. But it's still interesting if we are able to find a way to reconstruct mu in a model-independent way to test how much deviation is from the standard Poisson equation, like eta. So that is our motivation here. But in general, this is not easy to be done. For instance, we don't want to making use of the F sigma 8 or sigma 8 information from the galaxy correlations, because that contains some model dependence in the sense that it has to assume some fixed shape for the power spectrum, and we want to get rid of that issue. So is it possible to test mu? We found that if we combine the perturbation equation for the matter density contrast based on some general assumptions that are the same as before, if we combine this equation with the modified Poisson equation, then we are finally able to extract this combination of parameters omega m0 times mu, with the right-hand side essentially depending only on the growth rate f and the expansion rate e. With this m function quantifies the departure from the standard Poisson equation in the linear regime. We can only isolate this combination. This is because essentially one cannot find a way to measure omega m0 in a fully model-independent way. So the maximum set of parameters, the minimum set of parameters that one can measure is essentially this m quantity. And we also consider the case for a non-flat universe, because in that case, the modification of the Poisson equations got changed a little bit. And essentially what one can isolate is this new combination of parameters. But if we consider only sub-horizon scales, this m prime essentially goes back to m. So this means at sub-horizon scales, this m is valid for both flat and non-flat universe. So now the key point would be, how would it be possible to measure F and E in order to give predictions on this M quantity? For this E, we already seen before that it can be measured from the AP effect. So the key point would be, how it is possible to measure the growth rate in a fully model-independent way. So in order to do that, we make use of this free power method of this paper by Luca, where they jointly use the power spectrum together with nonlinear one-loop corrections, and also include the bispectrum. So they include this one-loop nonlinear correction in order to disentangle the growth rate f from the combination of f and the bias factor, and they use this tree-level bispectrum in order to enhance the precision. And the interesting thing is, in the end, it is possible to isolate this F in a fully model-independent way once we jump into the nonlinear regime and parameterize the power spectrum in terms of wavebands. So essentially, there's also no assumption on the shape of the power spectrum, and therefore no assumption on the initial condition of the universe. So in the end, the growth rate can be inferred from redshift space distortion, while E can be inferred from AP, and indeed, M is indeed a model-independent observable that we are able to measure. And now I would like to show you some results. These are some forecasting results on this M quantity. And here we did a forecast for a joint survey of Daisy and Euclid, where we mimic Daisy-like survey for relatively lower redshift range, while we mimic Euclid-like survey for the relatively higher redshift range. And in the best case, M quantity can be constrained at around 13%. And this is the main result of our paper. So we can see that M is constrained best somewhere in the middle, where the errors for the lowest redshift range and the errors for the highest redshift range is relatively larger. And this is simply because at relatively high redshift range, this is the number density of galaxies in each bin. The number density of galaxies is relatively low, and therefore we have a large sigma to noise ratio. Well, for the low redshift, this can be seen from the entries of the Fisher matrix elements, because at the low redshift, the survey volume is low, and sigma is inversely proportional to the survey volume. So at low redshift range, we also have relatively large errors. And we also consider the case if we add a prior on the growth rate, because we want to further enhance our constraining power. This prior on the growth rate, for instance, can be obtained if in the future we are able to reach a higher Kmax in the modeling of large-scale structure, for instance, by including higher order correlators in the large-scale structure estimation. And from here, you can see that the inclusion of the prior on the growth rate can significantly enhance the final estimation on this M quantity. Yeah, and this is another conclusion, which is measuring the ratio of these two, this M ratio, where Mi, Mj are two different M results at different redshift bins. Because by considering this ratio, we're able to get rid of this omega M0. And in that case, this R quantity is indeed an estimation of a violation of the standard Poisson equation. And furthermore, it is directly related to the standard test of gravity, which is proportional to this G dot over G. And this is essentially the case of the Jordan-Bress decay gravity. If this Rij deviates from 1, then we are confident to say, well, this mu indeed differs, it varies with time, and the standard Poisson equation is indeed violated. And furthermore, once you have this constraining on M, you're able to project the result onto any modified gravity theory or dark energy model. For instance, in the coupled quintessence scenario, if you remember, mu is essentially this 1 plus 2 beta squared. And if you consider M is constant along all the redshift bins, and for a constant coupling between the dark sector, they are exactly identical. So we can do a projection to project the result on M onto the result of the coupling constant. And here, this is our result. It is much weaker compared to the other results from the previous literature, but this is completely complementary to the previous results in the sense that we are obtaining the results from a completely different redshift range, the relatively low redshift range. Yeah. In addition to those old results from the CMB measurements. So this is essentially on the last slide I want to show you. This is basically a projection onto several other modified gravity models on the parameterized dark energy model, also the two Jordan-Bress decay gravity models with different fiducial values. And we didn't include any prior in the projection procedure in the sense that we want to remain our model independence. So from here, you can see, even though the result is less strong, but it's more robust in the sense that it is more model independent. Furthermore, if you can compare with previous results in the literature, we essentially get a similar result compared to the previous forecast for SK survey. Yeah, in the sense that we are both using the galaxy clustering information and obtaining the similar constraints. So with all this introduction, I will leave my conclusion here, and I'll be happy if you have questions.